Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 11 in our Paper 2 series, and it is advanced information listed for both the foundation chemistry and the higher tier chemistry. What we're going to be doing in today's booster is continue to look at those factors that affect the rate of reaction. So last time we had a look at temperature. What we're going to do this time is start off with concentration. First of all, when we talk about concentration, that is just a measure of how much solute is dissolved in the solvent. So a more concentrated solution has a greater mass of solute dissolved in that volume of the solvent. When we consider the pattern that we get with concentration, increasing the concentration increases the rate of reaction. If we're asked to explain why, then we need to talk about particles becoming more crowded. So in a higher concentration, the particles are more crowded and therefore they have more frequent collisions. Now that phrase might sound familiar because when we talked about temperature, we talked about more frequent collisions there. You are going to notice that this phrase, more frequent collisions, is just going to come up time and time again in this topic. So if you learn one phrase, and one phrase only to do the rates of reaction, more frequent collisions is the one to learn. So if we look at our little diagrams at the bottom, we can see on the left we've got a low concentration, on the right we have a high concentration. How do we know? Because if we look at the little red particles, then we have a greater number of them in the same volume, because our box is the same volume there. So we've got more of those red particles in the same volume, they are more crowded, therefore they're going to have more frequent collisions with our blue particles. So rate of reaction is going to increase. The reaction is obviously going to continue until our limiting reactant has been used up. Now if we're looking at our rates of reaction graphs, you are always going to be able to tell where that's happened because it's at the point that the graph plateaus or levels off. And what we find is that the amount of product we make is proportional to the amount of limiting reactant. So if they were to tell us that we have doubled the amount of our limiting reactant and ask us what happens to the amount of product, we would have to say it doubles. If they use the word halved, we would have to say it's halved. Don't just say it increases or decreases. If they're using one of these terms that has like a proper value associated with it, you've got to use a similar term in your answer. So because these are proportional, doubling the amount of the limiting reactant doubles your product. Halving the amount of limiting reactant halves the product. Our third factor, pressure. This is going to be in a gas that we are talking about, pressure. The pattern, if the pressure increases, then our rate of reaction is going to increase because the particles become more crowded, so they have more frequent collisions. If we look at our little diagram at the bottom, we can see that. So what we can see, we've got our 6 particles in our low pressure where we've got quite a nice high volume. As we then decrease the volume, the pressure increases, and you can see those 6 particles are now much more crowded. Therefore, they're going to have more frequent collisions. So, rate of reaction increases. The next factor is particle size. This is something we need to go careful not to mix up. When we break a material up into smaller pieces, then the surface area will increase. So if we start off with a large lump, and then we're going to break that up into lots of smaller lumps, these smaller lumps have a larger surface area than the one big lump, okay? Because what we've done there is we've exposed the bits that were previously kind of trapped inside. So the more we've broken it up, the larger the surface area will be. So a powder has a much larger surface area than a single lump of the same mass of material. How does this affect rates of reaction? When we increase the surface area, we increase the rate of reaction. That's because our surface area to volume ratio has increased. Because of that, there are more exposed particles, so there are more frequent collisions. There's that phrase again, more frequent collisions. So increasing surface area increases the rate of reaction because we've got a greater surface area to volume ratio, therefore more exposed particles, more frequent collisions. The last thing we're going to look at is the idea of a catalyst. When we talk about a catalyst, this is a substance that increases the rate of a reaction but is unchanged at the end. They're specific to a particular reaction and they could ask you to identify one. So what we would actually be given there are different bits of information. So we'd have 3, maybe 4, because if it could be a multiple choice, different substances. They then give us key information in a little table. So you would have something like our mass before, mass after. You could have colour at the start, we could have colour at the end, and we'll have a measure of the rate. So what we're going to find is when we're looking at these, we need to make sure the rate is increasing, because obviously a catalyst increases the rate of reaction. And then we need to make sure the 2 colours stay the same and the mass stays the same. What you're going to find is only one row on your table is going to have the same mass before and after, the same colour before and after, and yet the rate would increase. That's your catalyst. Any of the bits that are changing in terms of mass, colour, etc., then that's not a catalyst, because remember, it must be unchanged at the end of the reaction. So how does a catalyst affect the rate of reaction? Well, adding a catalyst increases the rate of reaction, as we've stated, because they're providing an alternative reaction pathway with a lower activation energy. So that just means that a greater proportion of those particles that collide with one another will exceed the activation energy and therefore have a reaction. One of the questions they do ask occasionally is they will give you a reaction profile and they will ask you then to plot the reaction profile you would expect for a reaction with the catalyst. So all you need to do there is make sure you've still got the same horizontal lines, so they still need to start and end at the same point, but you add a little curve that is lower than the original one they've given you with no catalyst, but it still connects to those 2 horizontal lines. So you can see there, this one here, okay, the little bluey purple line, that is our activation energy with a catalyst. It's lower, but it still must connect the reactants and the products line. If you do that, that's one nice easy mark. If there are bits that we've gone through in today's booster that you want to look at in more detail, then you can have a look at the C5 playlist on the main channel. Obviously, you should have a revision guide that can support you, your classwork notes, and of course, look at some past exam papers. See the types of questions they ask on rates of reaction, because they do come up quite frequently. And then, of course, don't forget to join us again tomorrow for our next daily booster.